So, oh, sorry. All right. So, unfortunately, feel pretty dumb. I just recorded a nice, probably about 3 hour video, and I didn't share my screen. Ooh, ooh wee. Um, but it is what it is. Um, so it's going to be a little bit of a man. I'm so upset. It's going to be a little bit of a different review. Unfortunately, because everything's already written. Um, I'm just, you know, didn't hit record. Anyways, so sorry about not having sessions this time around. Just been a pretty busy past couple of weeks, and I'm sure, as you can tell, a pretty big mistake like this, um, still busy. So man. Okay, sorry. All right, moving on. So to start off with sequences, I'm just going to do a lot of pointing today. Um, starting off with sequences, so we'll use purple. I just wanted to introduce a couple of theorems first. So theorem one, given a function, or I'm sorry, given a sequence, a sub n, we have a function f of x such that f of n equals our sequence, then the limit of our function is equivalent to the limit of our sequence. In other words, if I take the limit of f of x, it will also, as x approaches infinity, it will also equal the same value of the sequence as n approaches infinity. Our second theorem here is that the limit of the absolute value, if the limit of the absolute value of our sequence equals 0, then the limit of our sequence also equals 0. And the last theorem that we have to look at here is theorem 3. So the sequence r to the n, where n goes to 0 to infinity, converges if r is strictly greater than -1, but less than or equal to 1, and diverges for all other values of r. So here is the first example. Go ahead and give everybody this one right here. I'll go ahead and give everybody a second to write that down. Okay, so the sequence that we have here is 3n squared minus 1 over 10n plus 5n squared. So this is pretty straightforward. What I'm going to do is I'm just going to convert this into limit form. The limit as n approaches infinity of 3n squared minus 1 over 10n plus 5n squared. And we see in this first step, what we can do is we can actually pull out an n squared. We can factor out an n squared rather. And allows me to cancel that, simplify my sequence just a little bit. And then evaluating this portion of the sequence, any term that contains an n will be evaluated. So here and here. And both of those n terms converge to 0. So what we're left with here is 3 over 5. Okay, the next example we have is e to the 2n over n. And again, when I set it up in limit form, we see what we get is the limit as n approaches infinity of e to the 2n over n. And if we just evaluate this limit as is, we see that we end up with infinity over infinity, which is not allowed. So what I can do is I can actually use L'Hopital's rule. And what this demonstrates here is how L'Hopital rule applies. Remember, it's not ddn of the entire sequence. It's ddn of the numerator over ddn of the denominator. Taking L'Hopital's rule, we see that we get 2 2e to the 2n over 1. And then so taking the limit as n approaches infinity of our new function, or our new sequence, we get 2e to the 2n. As n goes to infinity, we see that this converges to infinity. Okay, so the next example I have for you guys here is above here, is -1 to the n over n. So again, what I do is I form it into a limit. And then within this limit, I know that this alternates. But what I can do is I can evaluate the absolute value in this case, leaving me with just 1 over n. And then I know that this converges to 0, so I know that the limit of this sequence, aka this sequence, converges to 0. All right, the last one for sequences here is I have the sequence -1 to the n. As I take the limit, as n approaches infinity, of -1 to the n. Unfortunately, this time I'm not able to do this because of theorem 3. It lies here. Sorry. No. The previous example fell under theorem 2, where we just have the sequence an, and in that case it was -1 to the n over n. But in this case, we just have Rn, negative Rn rather. And we see if we take this to infinity, like in the little diagram here, it never actually settles at a value 1 or -1, so we say it diverges. All right, so we'll start with a little introduction to series. If the series an converges, then the limit as n approaches infinity of our sequence an equals 0. And then, so with that, I introduce the divergence test. So the divergence test basically states that if the limit of an does not equal 0, then the series will diverge. Okay, so our first example here is the series for n squared minus n cubed over 10 plus 2n cubed. So what I can go ahead and do is I can just evaluate the limit. I can just go ahead and evaluate the limit. And we see we have 2 shared terms here. So I'm going to pull those out right here. And then I can cancel them, leaving me with just 4 over n and 10 over n cubed minus 1 plus 2. These 2 go to 0. The n terms go to 0. So we see it equals 1/2. And again, by the divergence test, right here, if the limit does not equal 0, then the series will diverge. And in this case, our series diverges. All right. So the next section we're going to look at is geometric series. Geometric series is represented in either one of 2 forms. Either the sum is n, n to infinity of ar to the n minus 1, or series n minus 1 ar to the n. And then the standard approach for determining convergence is to use this little formulation. Actually, this one here. But this is just a little proof. So if I take a and I distribute it and then separate the denominator here, and then I separate the denominator here, what I'm left with is a sequence. So if I take the limit of this sequence as n approaches infinity, we see there's no n term in this case. There is an n term in this case, so I'm going to rewrite it here. And then one more step, I see that we have a little bit of multiplication here, so I can actually break this up as the limit as n approaches infinity of r to the n. And following this diagram here, sorry, thank you. We know that Rn equals 0, so then this whole side becomes 0, leaving us with just Sn equals A over 1 minus R. And then so what this means is in order to determine convergence, all we need is A over 1 minus R. All right, so the first example I started with here is -2 times 5 over 9 n to the minus 1. So if you see, our first example here is in this form here, sorry. Our A equals -2, our R equals 5/9. So all I do is I just plug and chug, plug it into this equation here. 1 minus 5/9 gives me 4/9. 2 over 4/9 gives me 18 over 4, leaving me with the series that we were evaluating converging to -9/2. Okay. I really hope that was recording, but we'll see. I don't know. Got a weird pop-up on my computer. Oh, it's not a good night. Okay, next example of geometric series. So this one is much less obvious. Our original expression, I'll write it purple here. Is -4 to the 3n over 5n minus 1. So what I can do is I can actually, kind of following some of these little algebraic steps here, I can rewrite it in this form. 4n to the third to the n over 5n times 5 to the minus 1. And then doing a little bit of rearranging and then solving for this value here. What we end up with is we end up with our a term, our r, and then our n is right here. So in this case, a equals 5, r equals -64 over 5. And a nice little rule about the geometric series is that if the absolute value of r is less than 1, I'm sorry, greater than 1, then it diverges. And so in this case, -64 is indeed greater than 1, so our sequence diverges. All right. So our telescoping series is another type of special series that we'll see. And so the example that we're going to get, this one's just easier to show than it is to explain. So our original expression is here, 1 over n squared plus 4n plus 3. And then by partial fraction decomposition, we end up, and again, this is left as an exercise to the reader. 1/2 is our two constants, and then decomposed into I plus 1 and then I plus 3. These are just dummy variables, so don't worry about it too much. What I can do is I can pull out the common factor 1/2 and put it right here in the front of the series. Start to go away. Okay, a bunch of stuff is about to delete. We'll see what's about to delete. Yep, there we go. All right. So I can pull this out. And then I can put that right here in front of my series, leaving me with 1 over 1 I plus 1 minus 1 plus or I plus 3, 1 over I plus 3. And then if I just go ahead and write out the first few terms in this sequence, what I see is I get 1/2, 1/2 minus 1/4, 1/3 minus 1/5, 1/4 minus 1/6, and then etc. all the way through. And the cool thing about telescopic series is if you look a little bit further, if I were to write out a couple of more, we see I have a term to cancel my 1/4. Later on, there would be a term to cancel my 1/5. And then later on, my 1/6 as well. But the 1/2 and the 1/3 are untouched. So what I do is I just keep my terms and then write out my new expression. So these two terms are kept. This is our next. These are the remainder terms, at least the parts that get canceled. So what I can do is I can take that and I can now take the limit of this as n approaches infinity. And what we see is that this term goes to 0, and then this term goes to 0. So all I'm left with is 1/2 times 5/6. Therefore, our original series, 1 over n squared plus 4n plus 3, is equal to 5/2, or 5/12 rather. Cool. All right, and then this one here is a nice little combination of telescoping series and geometric series. So what I did is I went ahead and left this one as a reader, left this one as an exercise to the reader. But I will say, in order to get started, I can distribute my summation in to the parentheses, and then I'll get two separate sums. And then I will give my only other hint is that the answer is negative 3863 minus 3863 over 15. Okay, so we're going to come back to the harmonic series. No, I'll just go ahead and talk about it. Okay, so harmonic series essentially is anything of the form constant over n. And harmonic series will always diverge. So for example, here we have an example of our harmonic series, 5 over n. Again, this is n to the 1. If it was n to the 2, it's a different series, wouldn't diverge. But in this case, I can pull that 5 off and pull it in front. And now I'm just left with 1 over n. And we know that this diverges. So to introduce the next test, we have the integral test. The integral test states that if the integral from k to infinity of f of x dx converges, then the series a sub n converges. And then the second condition, or the second claim is that if the integral from k to infinity of f of x dx diverges, then the series diverges. So again, the integral converges, the series converges. And if the integral diverges, the series diverges. Okay, so this will kind of explain how the harmonic series, why harmonic series diverges. Because using the integral test, again, this is the same example as we had from before. I have the sum from n equals 1 to infinity of 5 over n. What I can do is I can convert this from f of n to f of x. Leaves me with 5 over x. I evaluate this integral and I see that I get 5 natural log of x on the bounds from 1 to infinity. And we see that this equals infinity. Therefore, because the integral diverges, the series diverges. Another example of the integral test here. I have the sum as the sum from n equals 1 to infinity of 1 over n squared, which equals the integral from 1 to infinity of 1 over x squared. I'm going to leave this one up to the reader as an exercise to verify that my integration was correct. But if you do all of the steps correctly, what you should see is that this integral converges to 1. All right, last little bit. I left another exercise for you guys to try. Use the integral test to verify whether or not this integral converges, and if it does converge, what does it converge to? The series n equals 1 to infinity of n times e to the negative n squared. All righty. So the next topic we're going to talk about is the p-series test rather. So for k greater than 0, the series n equals k to infinity of 1 over n to the p converges if p is greater than 1. And this is kind of pretty common for all of the tests. Again, they're just tests. They're just whether or not does the series converge or diverge. But if the series converges, then you have to finish the problem all the way through using maybe another technique. And you'll see what I mean by that later. Finish and find the convergence value. And if it diverges, you're done. And then the same two conditions apply for integration here. So if the integral from k to infinity of 1 over x to the p dx converges, where it converges if p is equal to, greater than 1, and diverges if p is less than or equal to 1. Okay, so first we have the sum is n equals 4 to infinity of 1 over n to the 7th. Again, by our p-test, it's convergent if p is greater than 1. In this case, p is equal to 7. Therefore, it's convergent. And now we have to finish it out. So what I'm going to do is I'm going to change it to an integral because that's easier to evaluate. So I have the integral from 4 to infinity of 1 over x to the 7th. And again, if you do the integral correctly, you'll see that we get an improper integral, meaning that somewhere it's undefined. So what I need to do is I need to formulate it like an improper integral and set my equation, take the limit as t approaches infinity of the integral from 4 to t of 1 over x to the 7th. Evaluating that, I get 1 over 8x to the 8th. From 4 on the bounds from 4 to t, and we see that this converges to negative 1 over 64. Therefore, because this integral converges, we say that our series converges to 1 over 64. So a case of the second condition, I have the integral I have the series n equals 1 to infinity of 1 over square root n. And so in this case, this can be rewritten as 1 over n to the 1/2. And in this case, our p is less than 1, which is less than 1. Therefore, diverges. And we're done. All right, so this is the limit comparison test, and I think the ratio test, it's not in my notes as the ratio test, I'm not 100% sure. But the comparison test states that given the series A and B, with A and B being greater than 0 for all n, and A being less than or equal to B, then if the series Bn converges, then An converges, and if An diverges, then Bn diverges. And what this little test says is, given A and B, where A is greater than or equal to 0, and B is greater than 0, greater than or equal to greater than 0, we define C to be the limit of the ratio of our two sequences. And some little facts about C, what C tells us, rather, is that if C is greater than 0 but finite, or less than infinity, yeah, so C is greater than 0 but also finite, then either both converge or diverge. So seems confusing? Don't worry, we'll talk about it. So first, I'm just going to apply the comparison test here. Given our initial expression here, we have e to the negative n over n plus cosine squared n. And again, as noted, this is our an. And what I need to do is I just need to clean up this denominator to find a quote unquote bigger function or bigger sequence. So what I can do is I can actually just drop the cosine, leaving me with just n. And then what I can do is I can let n equal 1 in this case for the denominator, or just change it to 1. It makes it a bigger sequence, leaving me with e to the negative n. Okay, so with the comparison test, now all I have to do is determine what this converges to, if it converges. And so what I have is the series from n equals 1 to infinity of e to the negative n. Then I can change this into an integral on the bounds 1 to infinity of e to the negative x. I know that this is an improper integral, so what I'm going to go ahead and do is take the limit as t approaches infinity of the integral on the bounds 1 to t of e to the negative x. And I'm going to evaluate this integral here, giving me e to the negative e to the negative x on the bounds 1 to t. And this equals e to the negative 1. So what I see is that b converges to 1. I'm sorry, b converges to e to the negative 1. Therefore, our original expression, e to the negative n over n plus n squared, or cosine squared n, converges to e to the negative 1. All right. So the next test that we have to do, or the next little example, our original example here, 4n squared plus n over the cube root of n to the 7th plus n cubed. I need to find a function bigger rather. So I'm just going to clean up that integral. I'm just going to drop the 4 and drop the n, leaving me with just the n squared. And then I'm just going to drop this n cubed term, leaving me with just n to the 7th. And then I can clean this up one more time, leaving me with just 1 over n to the 1/3. And the way this works, I can rewrite n squared as n 6 over 3 over n 7 over 3. This equals n to the 1 over 3, negative 1 over 3, which is the same as this right here. Okay, so I'm just going to set that aside. And then if we remember back up here to our rule, we have an over bn right here. So if this is my an, the original expression was my an, and my new expression is my bn, I'm going to divide the two. And then I'm going to rearrange it here. And then lastly, what I'm going to do is I'm just going to clean everything up. This gets sent up to the numerator. That's where we get this expression here. I'm going to clean everything up. So when I multiply here, I'm sorry, not multiply. When I add these two powers, I get 7 over 3 plus n to the 4 over 3. And then what I'm going to do here is on the top and the bottom, I'm going to divide by not divide, but I'm going to factor out n to the 7 over 3, and then likewise for the bottom. But in this case, the way this works is what I can do is I can factor out the n to the 7th on the inside, and then pull it out as n 7 over 3. Because if I multiplied this back in, the 3 would cancel with this 3. This 3 would cancel with this 3. Oops. Oh, give it a second. Anyways, and that would leave me, that would allow me to cancel these two n terms. There's a 3 here. There we go, it canceled. It went away. This 3 and this 3. But anyways, that would allow me to cancel my two n to the 7/3. And then all I need to do is, again, we're taking the limit. Remember, right here, we're taking the limit. So what I'm going to do from there is I'm going to take the limit of this expression. And we see that both of the n terms approach 0, leaving me with 4 over the cube root of 1, which is just 4. So 4 equals C. And this meets the condition, remember? 4 needs to be greater than 0, but also finite. I'm sorry, C needs to be greater than 0, but also finite right here. So we know that we have formulated our series correctly, and because we found this common factor C here, we do know that it's either convergent or divergent. So now we need to figure it out. And because we did all this work, and we kind of made life easier on ourselves, if we remember back when we established our equations, I can do one of two things. I can determine this limit and see what this converges to, or I can make my life easy and just take the limit as 1 over n to the 1/3 converges. I'm sorry, the limit as n approaches infinity, because remember, this is our an, this is our bn. So I'm just going to evaluate this, because if bn converges, then an converges. So back to my limit process here. Here is that bn. And what I can do is I can evaluate this as an integral. And I'm going to leave this as an exercise to you guys to prove. But this integral will diverge. So by the integral test, the series diverges. And because bn diverges, an diverges. Therefore, our original expression also diverges. Alrighty. So the alternating series test. Given the series a sub n, where a sub n is equal to -1 to the n times bn, there are two conditions that are put on bn to determine whether or not our series converges. So the first condition is that the limit as n approaches infinity of b sub n equals 0, and bn should be a decreasing sequence. So the example we're going to take a look at, if both of those, if both of these conditions here are met, then an converges. And then we need to figure out what it converges to. Okay, so the first example I'm going to start with here is cosine n pi over square root n. And something to note is that cosine n pi is just a fancy way of writing the alternating series sequence -1 to the n. So what I'm going to do is I'm just going to go ahead and replace those right here. And I see that this is my new sequence. And from that, what I can pull from that is that my Bn in this case is 1 over square root n. Okay, awesome. So what I'm going to do is I'm going to follow my two conditions. The limit as n approaches infinity of b sub n must equal 0, and I need to find out if it's decreasing. As I'm sure most of you guys know, when I take the limit as n approaches infinity of 1 over the square root n, we see that this limit converges to 0, therefore condition 1 is checked. Now we need to see if this is a decreasing sequence. So I take this sequence and I write out the first couple of terms, and I see that 1 is bigger than 1 over, like 1.14 or something, is bigger than like anyways, you get the idea. This would be 1, and then this would be significantly smaller. Therefore, it's a decreasing sequence, as in the numbers get smaller as we go that way. So the last thing I leave to you guys is, because we should be pretty confident at this point, n equals 2 to infinity. The last thing you need to do for this one is determine what this converges to. Both of the conditions have been checked, so we do know that it is a convergent sequence. Now, determine what it converges to. Alrighty. And now taking a look at the second case, or not the second case, but an alternative case. Let's take a look. I have negative 1 to the n squared, over n squared plus 5. So what I can do is I'm just going to pull that little alternating sequence portion off so that I can have the -1 term here and my bn term here, which is this portion here. And then I need to do both of my tests. So the first condition is whether or not bn equals 0. So I'm going to take the limit as n approaches infinity of n squared over n squared plus 5. And in this case, again, up to you guys to verify, but this sequence, this limit equals 1, which does not equal 0. Therefore, we can stop. The conditions of convergence have been met, that have not been met, rather, and this sequence will diverge, series will diverge. Okay, so that was the last example I had for you guys. The last thing I'm just going to talk about is absolute convergence. So in this case, when you have a series, if the absolute value of the series is convergent, then we say that an is absolutely convergent. Or if the absolute value of the series is divergent, then it's conditionally convergent. And what we need to do is we need to just do a different test. So in this instance, the absolute convergence test is not valid, and we need to look at something else. Okay, so I'm sorry if this wasn't a super thorough exam review. Like I said, I recorded, took me about 3 hours to record all of this. And I didn't share the screen, so that's just an audio of me talking, and I don't think that's very helpful. But if you have any questions about the review, please feel free to reach out before your exam. Best of luck to all of you, and I look forward to talking to you guys before the final. Bye.